Hello and welcome to our short presentation of our research with the title Autonomous Cycle Time Reduction of Robotic Tasks Using Iterative Learning Control. My name is Lorenz Halt and I'm a staff member of the Fraunhofer Institute for Manufacturing, Engineering and Automation from Stuttgart, Germany. In this research, we combine state-of-the-art iterative learning control with an industrial robot environment and a new idea. Our main motivation stems from the experience that programming industrial robots is a very time-consuming task. Even relatively simple robot programs require a lot of effort to be designed and to be optimized, especially if every second counts. The greatest challenges arise when a robot motion is negatively affected by the dynamics of the previous motion. An initial proof of concept is usually very quick to program. However, much additional time, effort, and expertise is required to speed up this program to meet industry's cycle time expectations. In addition, the robot system is not running in production during this programming phase, and while many contributions had been made for fast and easy programming, we found that optimization of a given robot program is underrepresented. Our goal is to automatically speed up a given robot motion while the system is productive and remains within acceptable and tight tolerances even during transient phases of this automation. Further, our approach shall be directly applicable to a wide range of robotic tasks and programs. It should be easily and straightforwardly integrated into any robotic system. For the use of iterative learning control, we exploit the fact that industrial production tasks are highly repetitive. The robot constantly repeats its production cycle. Iterative learning control, or short ILC, generally tracks a robot control deviation or control error during a cycle and uses this experience to provide specific feed-forward signals for the next cycle. During typically 10 to 15 iterations, ILC converges to an optimal specific feed-forward signal capable of compensating systematic disturbances. The very small number of trials and the simplicity of ILC made it an excellent technology candidate. Nevertheless, fast converging and thus aggressive ILC tends to overshoot during these optimization trials. Therefore, we had to combine ILC with yet another idea. This idea is probably the most important contribution of this work. Instead of optimizing ILC for maximum speed right from the beginning, we start with an initially low reference speed of the robot motion. ILC is then used to set up a feed-forward signal for optimal reference tracking. When the error of the motion controller, including the ILC feed-forward, is within a certain threshold, we gradually adjust the motion reference for faster motion. In other words, we close an outer stepwise reference adjustment over an ILC optimization. We found that our reference adjustment ILC scheme is able to outperform the standard ILC in terms of transient overshoots, while being comparable in terms of overall convergence. To evaluate our results, we performed two experiments using an externally controlled UR5 robot. First, a simple linear motion task, and second, a contact force stabilization task. For the linear motion task, we started with a very slow reference of about 12 seconds. Within 100 runs, the execution time was reduced to about 3 seconds. The total optimization time for these 100 iterations was less than 20 minutes. We can see that the reference fitting peaks in the error norm, but we can also find a relatively homogeneous decrease in execution time. We obtained quite similar results for the force stabilization tasks. In this case, we started with a conservative motion in free space up to a threshold of 10 newtons, with an execution time of about 20 seconds in this video or 50 seconds in our research. After 100 iterations, the execution time was reduced to only about 5 seconds. The algorithm had successfully learned to accelerate the motion in free space and decelerate right before impact. To conclude my talk, we presented a simple reference adapting scheme with an intermediate ILC optimization. Its goal is to reduce the cycle time of industrial robot during production and within production tolerances. We have shown that the proposed scheme can be well generalized to various tasks in robotics. In the near future, we hope to move forward to more sophisticated ILC to deal, for example, with multiple input, multiple output systems, and to add this scheme to other post-programming optimization ideas. Thank you so much for your attention.